let's move one step ahead and find the pin reaction over here at the hinge where this rod of mass m and length L is pivoted. It is hinged over here. This is a uniform mass rod, and we know that is how to find the centripetal acceleration and tangential acceleration of this rod of the center of mass. Now we are comfortable with that. Let's once again hurriedly revise how we have found the centripetal acceleration and tangential acceleration of this, and why we have found to find the pin reaction over here. When we have to find the pin reaction over here, then certainly that is we shall be requiring some kind of force. And this force over here, any reactionary force, it will have two components. One is Fx, the other will be in Fy. So these two forces will be there, and then from there we can find the result. So now if we need to find Fx and Fy so that we are able to find the pin reaction over there, so it means we need to find what is acceleration of center of mass along x-axis and what is acceleration of center of mass along y-axis, because from there we can find the force along x-axis, and from here we can find the force along y-axis. And then how we found the centripetal acceleration and tangential acceleration. In this case, when this rod had been when initially the rod was here vertical, a gentle push was given and it starts falling like this. The first thing we have to see is that the motion is going to be non-uniform circular motion. If this is going to be non-uniform circular motion, there is going to be tangential acceleration as well as centripetal acceleration. So we are going to have two accelerations. One is centripetal acceleration, which you know that is v square upon r, or v is equal to r omega. So r omega square upon r, that is r omega square. And apart from this, a tangential is going to be r alpha. So we have these two accelerations if the motion is non-uniform circular motion. How do you find a centripetal? This a centripetal, it was found using energy conservation principle. So now, how we found the conservation of mechanical energy? We have said that is from here to here. When it goes over here, the center of mass goes from here to here. That is, center of mass is that point where the whole mass is concentrated. So m is over here. So we had done, that is mgh, loss of potential energy, is equal to half I about O into omega square. From there we have found omega, and from there, once we found omega over there, then the centripetal acceleration we know it is going to be r omega square. So r omega square, that is we have found the AC. So remember, we had found the centripetal acceleration using the conservation of mechanical energy principle. Loss of potential energy is equal to half I omega square. From there we found omega. Then acceleration of center of mass is equal to r omega square, whereas the radius, that is from here to here, that is L by 2. So once centripetal acceleration is known, now we go to tangential acceleration. Tangential acceleration, we know AT is equal to r alpha. For tangential acceleration, what the relation comes out to be in our mind is AT is equal to r alpha. So it means somehow if alpha is known, so our job is done. So from where we can find alpha? Alpha is also associated with torque is equal to y alpha. So from here, that is we say, if we have to find torque about this, so this was mg acting at this distance. If this is L by 2, so this by L by 2 cos theta and this by L by 2 sin theta. So what we have done? We have done mg into L by 2 sin theta is equal to I about O, that is I about O into alpha, and I about O about this axis is ml square by 3. We have done it moment of inertia. When we found moment of inertia, this L and this L is same, ml square by 3 into alpha. And this I, either you can use the parallax theorem or you directly know, the moment of inertia of a thin rod of uniform linear mass density has a moment of inertia ml square by 3 about an axis passing through one of its ends and perpendicular to its length. So we have used torque is equal to y alpha. So from here alpha comes. Once we get alpha, then tangential acceleration, obviously that is going to be tangent to this. This is the radius. So AT is over here. So we have found AT also, we have found AC also. Now let's go to how to find the pin reaction over here. Once the tangential acceleration is known and centripetal acceleration is known, so now our next target is how to find the pin reaction over here. For that, what we do is, over here we shall be needing Fx and Fy. So let's break these accelerations along x and y axis so that we can find the net acceleration along x axis and along y axis. We see that this is theta. So this and this line, that is parallel. So this is also going to be theta, right? So if we break AC into rectangular components, one is going to be this way, the other is going to be this way. Let's draw it over here. This on this line only, so that it is easily visible. So I have drawn slightly over here, that is along this axis. It is AC, it is going to be sine theta. that is the component of centripetal acceleration this way is going to be AC sin theta, and this way is going to be cos component, that is centripetal acceleration into cos theta. Its job is done. Now this is theta, this total angle is 90, so this is 90 minus theta, this and this is 90, so this is also theta. So when this is theta, this tangential acceleration, it will have components. One is over here, that is 80 into cos theta, and this is going to be 80 into sin theta. AC and AT we have already found out. So now this is x-axis and this is y-axis. So what we do is, now we find A net, this minus this, acceleration net along x-axis, and if we add these two, this is acceleration net along y-axis. This is x, this is y. So this minus this will give you the acceleration along x-axis, and this plus this, both the acceleration in downward direction, so this plus this gives you the acceleration along the y-axis. So what is this? This is acceleration of center of mass, right? So we have found the acceleration of center of mass along x-axis also and along y-axis also. Now let's draw the free body diagram of this member or of this rod and see that is how the force will be acting. So this is rod over here. Let's say this pin applies a force onto this. We know that the acceleration is this way, so it must be applying force this way only, that is Fx. This pin must be applying force this way only because we see that is center of mass is being accelerated in this direction. So over here the pin must be applying the force onto this rod in this direction only. As far as the Fy is concerned, you can take in any way, that is this way or that way. Let's take it this way and we'll come to know what is the direction like. And over here we have mg also, which is acting in this direction. These are forces which are being experienced by the rod. One is, this is force along x-axis and along y-axis. One is the force which is applied by the pin, component of that force along y-axis. See, Fx and Fy, they are both the forces which are being applied by the pin. We have broken the force which is applied by the pin along x-axis also and along y-axis also, because any force can be broken along x and y components. So we have broken it along two components. Mg will certainly all the time act vertically downwards only. So we have two forces. One is the reaction over here on the pin and the other is mg. When the reaction of pin is broken, so that makes two forces. One is along x-axis, the other is along y-axis, and mg is acting vertically downwards. Now we see, let's say that is along x-axis. Force is equal to mass. Mass of center of mass is m, and what is the acceleration along x-axis? We have found this. That is A net along x-axis. So from here we know m, we know A net we have found out. So from here Fx can be found out. Let's find what is the force along y-axis. So along the y-axis we see that center of mass is falling down with the acceleration, that is this plus this. That is A net y is the downward direction. So it means the net force has to be in the downward direction. That is, we are applying F is equal to ma, Newton's second law, net force is equal to mass into acceleration. Mass is constant, so this is for the constant mass bodies. So for this we say mg, downward force, minus upward force, minus Fy, because the net acceleration is downwards. Net acceleration is downward, so it means this force should be greater than this force. So mg minus Fy is equal to m into ay a. So mg minus Fy is equal to m a net into y. This is over here, we put the values. So from here we can get the value of Fy. Once we get the value of Fy, suppose the Fy comes out to be positive. If the value of Fy comes out to be positive, it means the direction of Fy, what we have assumed, is right. If this Fy comes out to be negative, it means the direction of Fy, what we have assumed, is not in this direction but in this direction. The same thing can go for Fx also. So from here now we have found Fx also, we have found Fy also, we have found Fy because we know mg also, we know m also, we know acceleration net along y-axis also. From here Fx and Fy is known. So once Fx and Fy they are known, we can find the resultant of these two forces this way. So once this resultant force, that is F net, is known, then certainly this is the force which is being applied by the pin onto this rod, and this rod will do the reactionary force in the opposite direction. This will apply a reactionary force in the opposite direction at the same angle. Our basics of vectors, you can find the angle also theta. That is, if this is the case, so this is Fx, so this is also Fx, and this is Fy, we are taking it. So tan theta in this case is going to be perpendicular by base, that is, it's going to be Fx by Fy. So we can find the theta also, whatsoever the case may be. Once we find theta, if this is a resultant force, this is a net reactionary force, that is a force which is being applied by the pin onto this rod, then obviously the pin will experience a force in the opposite direction. To have a reaction, there is equal to opposite reaction. So this way we can find the reactionary force. Now there could be two cases. One case is when the rod was over here, it was gently pushed, so it comes over here. So when it comes over here, then it is falling like this. Over there it has some omega. So right now it has some omega. What if the rod has not been released from here, but the rod is released from here? Please understand. That is, now the rod is not released from here, it is released, it was being held over here, and now it is released, and now it is asked, that is, what is a pin reaction? Now it is asked, that is, what is a pin reaction if it has been released from here? So the case what we just did, it was released from here, and over here, when it reached over here, it had some omega. Now we are taking the case when it has been released from here. So right now omega is equal to 0. So how it will affect the pin reaction over here at the hinge P? That is how it is going to affect it. Now the thing to understand is that is over here, because right now there is no omega, angular velocity is not there. So that's why when the angular velocity is not there, it has just been released. It means there will not be any centripetal acceleration. There is not going to be any centripetal acceleration, and the only acceleration it is going to be tangential acceleration, because this torque will always be acting. This torque will be acting at this moment. That is, mg will be acting. This is L by 2. So this is torque is equal to I alpha if we apply about point P. So I is also about point P, alpha is also of this body. So torque about P is mg into L by 2 sine theta. It is same thing what we have been doing earlier also. So it is ml square by 3 into alpha. So from here we find alpha. Once we find alpha, then it is going to be only a tangential. That is tangential acceleration going to be there. That is tangent, that is perpendicular to this radius, that is L by 2. So now AC is not there. The only difference is that when it is released from here and it reaches over here, it will have AC also and it will have AT also. But if it is released from this point, then it will have only AT, rest all the things remain same. That is over here. Now you will break this AT into two components. This is going to be theta. So this is going to be component of AT x, and now this is going to be AT axis tangential y component along y axis. And same way, what we had done over here, this is one is, we know that is center of mass, it is going to have, one is tangential acceleration along x axis, the other is it is going to have tangential acceleration along y axis. Mg is going to act in this direction. One is you can take Fy in this direction, let's say, and Fx is in this direction. So now you can say is along the x-axis, if you see, that is Fx is equal to m into a tangential, which you have already found, a tangential along y-axis, a tangential about x-axis, a tangential about x-axis is known, m is known, so that's why you can find Fx. Similarly along y-axis, if we see, that is, we write mg minus Fy is equal to m into a tangential along y-axis. This is known, mg is known, so from here we can find the value of Fy. So Fy and Fx is known, so from here you can find the resultant force, and that is the reactionary force by the pin onto this rod.